Welcome. Today we're going to talk about Rolle's theorem and the mean value theorem, which is sometimes abbreviated MVT. So actually it's one of the three theorems we do by initials here. We've already learned the intermediate value theorem, we've learned the extreme value theorem, and this one is the mean value theorem. So this is what we'll talk about today, along with Rolle's theorem. Now, I'm also going to prove the mean value theorem using Rolle's theorem because they're really actually the same thing, just sort of rephrased, and then we'll give kind of an application of it. So, what is Rolle's theorem? Rolle's theorem says if you get a function that's nice, if it's continuous on a closed bounded interval, and it's differentiable on that interval, except the endpoints, since we don't really know what happens there. Now, if the function agrees at the beginning and the end, there's a place in the middle where the derivative is 0. Let's draw a little graph of that over here. So, if the function agrees at the beginning and the end, and it behaves nicely, there's no way you can go from here to here without flattening out somewhere. Flattening out means the derivative is 0. You can't do it. You can't go from here to here without being flat somewhere, unless you jump. Unless you have a problem with the derivative somewhere, then you can. Now, if there is no problem with the derivative, if it's continuous, there is always a place where the derivative is 0. The mean value theorem takes this one step further and says, let's get rid of this condition. Same starting, if it's continuous on the interval, if it's differentiable on the interval, then regardless of the start and stop, there's going to be a place in the middle where the derivative is equal to the secant slope. Now, let me illustrate what that means. So here's a point, suppose it starts here and ends here. The secant slope is the slope between those 2 points. What the mean value theorem says is no matter how I draw a function from here to here, if it's continuous and differentiable, somewhere along the line we'll have a slope like this. It's kind of like the intermediate value theorem in concept. Intermediate value theorem said if you start and stop here, you got to pass through each value. There's no way you can do it. This one says if you start and stop here, you got to pass through some place that has that slope. So, let's try drawing a function that starts and stops. No matter how I do it, there's going to be a spot with that slope. Right about right there. Has the same, that tangent slope is the same as this secant. How about down here? Right there. And actually right there. There are 2 of them. This theorem doesn't say there is one spot. It says there is a spot, which means there could be more than one. There could be 30. There could be 1,000,000. There could be an infinite number. But there's at least one. Now, as I said, I'm going to prove this theorem using Rolle's theorem. I'm going to prove the mean value theorem using Rolle's theorem. So what you do is you say, let's take a function f that works on these first 2 conditions, which are the same in each case, and let's twist it around so that we can get this condition and then see where we go. So, suppose we've got a function that's continuous on the interval and differentiable on that interval. We're going to ultimately need the slope, so let's let m be the secant slope that's going on. Our trick is we're going to let g be a function f of x minus m times x. What we're doing is we're taking the original function and subtracting the slope times x. Now, why are we doing that? Because if you notice, g of b minus g of a, just plug them in. You get f of b minus mb minus f of a minus ma. I'm just plugging in. I'm going to rearrange the terms right here. Then I'm going to expand what m is. M, remember, is a constant. It's this slope. All I'm doing is taking this and expanding it out, and I get f of b minus f of a minus that slope times b minus a, because that's right there. Now, when I have this times this, divide by that. This and this are the same, aren't they? So I'm going to cancel right here and right here. What did I all get? I got f of b minus f of a subtracting the quantity f of b minus f of a. So I got this minus itself is 0. That means, for this weird function g, Rolle's theorem holds. Rolle's theorem says if g of b minus g of a is 0, or rather it just says if g of b equals g of a, then there's a place where the derivative of g of c is 0. But what's the derivative of this? it's the derivative of f minus, that's a linear function, so minus m. So f prime minus c, f prime of c minus m is 0. Bring that over, so f prime of c is m. So there's a place where the mean value theorem holds. If this kind of didn't sit so well, it's okay. These are abstract concepts. These theorems are used to prove more powerful results. They're not really direct applications that we use, but maybe we can just illustrate. Here's a function, e to the x, and we're going to put it on this closed bounded interval. It's differentiable everywhere there. It's continuous everywhere there. Now, if that's the case, is there a spot where we have the secant slope, where the tangent slope of the function is equal to that secant slope? So that secant slope is f of 2 minus f of 0 over 2 minus 0. Do the algebra, you're going to get here. So I want a place where the derivative is that value. But the derivative of e to the x is e to the x. So I want a place where e to the c is that. Take the natural log of both sides, and you get right here. That c is the answer. That's the c that the mean value theorem is looking for. Notice the mean value theorem didn't tell us what c was. We have to do algebra to find that out. It just tells you there is a c. And look, it fits pretty well on our graph, right about there between 1 and 2. It's got that slope of tangent right there, and that's the same as this one. There's no way to go from here to there without passing through a spot that has that slope. Till next time, this is Dr. J.